In the previous clip, I've shown you that ratio tests sometimes can be used to prove convergence of a power series. Here I will discuss a more general theorem about convergence of power series. So suppose here we have a power series built upon, constructed using a fixed sequence Cn, and then we have the following. The first is that if if the series converges when x equals a b, then it will also converge for all x's which are in absolute value smaller than the absolute value of b. Yeah, suppose you can show that the power series converges for x equal 2, then you also know that your power series will converge for x equal to minus 1, since the absolute value of minus 1 is smaller than 2. Well, the second part deals with divergence. So if we would know that the power series diverges for some element, x equal b, then it will also diverge when the absolute value of x is larger than b. This basically shows that power series are convergent on symmetrical intervals around 0. A proof goes as follows. So first we're going to show the first statement in the theorem. So we're going to show that if Cn xn, the series, converges for x equal b, then also if x in absolute value is smaller than b. Well, how can we show this? Well, suppose now that we have that the sum of n equals to 0 to infinity, c and b to the power n converges for some b unequal to 0. Yeah, and why do we assume that b is unequal to 0? Well, if b is equal to 0, then we cannot find an x in absolute value smaller than the absolute value of b, which would be 0. Yeah, notice that this series is always convergent for x equal to 0, right? B equals 0. It's trivial to show that the series converges. So now let's assume that C and B and the series um, converges for some b unequal to 0. So what we then in particular have is that the sequence C and b to the power n should have a limit 0. Well, why is that? Well, we've seen that series can only converge if the consecutive elements in the sequence on which the series is built upon, that this limit equals 0. So we should be able to show that the things that we keep adding to the partial sums become arbitrarily small. So this was a necessary condition for convergence of the series. Okay, so we have the following. So for n large enough, suppose that we have a capital N, and for n large enough, that means that for a small n larger than some capital N, we should have that the absolute value of C and b to the power n is smaller than 1. Well, since the sequence is converging to 0, we should at least have that for n large enough, the absolute value C and Bn stays away from 1. It should be smaller than 1. Right? So now we can look at all these indices n larger than capital N, and look again at C and B of C and Xn absolute. And we now perform a trick. We multiply xn with b and b to the power n, x to the power n with b to the power n, and we divide by b to the power n. Yeah, so since b is unequal to 0, we can do this. And we look at this term in absolute value, right? So what we can do now is take out the factor absolute value c and b to the power n, and what is remaining is the absolute value of the ratio of x and b to the power n. Okay, but we have shown that for these large values of n, we know that c and b to the power n in absolute value is smaller than 1. So what we get here is smaller than x divided by b absolute to the power n. Yeah, and this holds if only x is unequal to 0. Okay, now assume that x in absolute value is smaller than the absolute value in b. Yeah, just as in the statement, right? So suppose now we take an x for which the absolute value is smaller than the absolute value of b. So this means that x belongs to the interval minus b, b. Then in particular, we see that x divided by b absolute is smaller than 1, right? So divide left and right by the absolute value of b, and we get x divided by b absolute is smaller than 1, right? So if we look at the series starting with n equals 0 and to infinity, x divided by b to the power n is convergent, right? As a geometric is convergent as a geometric series, right? Okay, but then we can sum up over all terms here, x divided by b to the power n. This means that we can also sum up over all these elements here on the left. So what we deduce is that also the sum of over n equals capital N to infinity of c and x to the power n absolute, that this also converges, right? So in particular, if we just take the first capital N minus 1 terms, or capital the earlier terms also in this sum, so we start up summing from n is 0 to infinity, we just add up n additional terms, right? Compared to the thing that is written here. So we let now n start with 0. Then we just add finitely many terms here on the right, which means that also this sum must exist, right? So also this sum exists. And what we then see is that if the sum over the absolute value of c and x to the power n exists, then we have an absolutely converging uh, a converging series. So which means also that the series itself, the sum over c and x to the power n, is also convergent. So the proof consists of two parts, basically. First, we show that the series itself in absolute terms is smaller, is dominated by a geometric series, which we can sum up, and then the series itself in absolute terms is converging, so we have absolute convergence, which implies convergence. Okay, now the second part. Suppose we have that the series is diverging for some d in R, right? So suppose this series is diverging for some d in R, then we will show that the power series formed by including x diverges if only the absolute value of x is larger than d. So how does it work? Well, basically, it's a consequence, an easy consequence of the first part. Suppose, on the contrary, yeah, of the first part. Suppose, on the contrary, that we would have a convergence of n equals 0, the sum of n equals 0 to infinity of Cn x to the power n for some x in absolute value with absolute value larger than d, then we would have that the series um, build up from d would be absolutely converging for d, and therefore the series n equals 0 to infinity Cn d to the power n would be converging. Yeah, but clearly this is not what we assumed. We assumed that the series with d is diverging. So this gives the desired contradiction. And this completes the proof.